Well, that's taking away an electron. Let's talk about adding an electron now. Now, if taking it away was positive, then adding an electron would give you what kind of energy? That would be what? Negative energy. Okay, so this would be the nonmetals, like chlorine, for example. So if I add an electron, now chlorine would like an electron, right? So we're like, yes. So we're like, all right. So energy is released when that happens. Now here's our trends in electron affinity. Okay, this one is a little bit difficult to understand like a full trend. There's really kind of not one. Like we talked about with the corners of the periodic table, we don't really have that one here. Okay, so what we can say is, let's talk about left to right. So what do those negative numbers mean? Well, lithium is minus 60, and let's do fluorine is a minus 328. Okay, so there's this electron. It's out for bid on eBay. And lithium's like, hey, you know what? I could probably use another electron. I mean, I have an S subshell. I could fit 2 electrons. I have 1. I guess I could take another one. So lithium says, all right, I bid $60. I'd be willing to pay out $60 for that electron. But what about fluorine? Okay, fluorine's like, whoa, I am so close to being like a noble gas. I so want that electron. So fluorine's scrounging all around the house looking up, okay, what have I got? What have I got? I'm going to take every dollar that I have. I'm going to bid $328. That's all I've got. So who wants the electron more? Fluorine. So the electron affinity is higher, right? So the bigger the negative number means, woo, I really want that electron. You know what affinity means, right? It's like, ooh, so you really want it? Like, ooh, if I have an affinity for chocolate, that means, whoo, I really like chocolate. Okay, so affinity for electron affinity. Ooh, I really want electrons. So who wants electrons most? Okay, that's what we're saying. So the bigger the negative number, the greater the electron, that nonmetal wants that electron, right? Does that make sense? And of the halogens, you know, we kind of vary up and down, but fluorine is a very reactive halogen, by the way, and we'll see that later here. Fluorine is very reactive compared to iodine. And, oh, what about the noble gases? Woo! Noble gases are greater than 0. Wow! What does that mean? They're like, I don't want that. So there's this electron out for eBay, right? And the noble gas says, are you kidding? I'm not paying a thing for that. If you want to get rid of it, you're going to have to pay me to take it off your hands. Okay, so that's what the noble gases are like saying. All right, well, if you look at there, not only do we have that with going on the noble gases, but there's 2 kind of little anomalies. They're kind of like 2 little columns. Now, why is that? Here you've got lithium, hey, willing to pay $60 for that electron. And beryllium's like, I'm not paying anything. So why do you think that would be? Does everybody see that? Yeah, because isn't this the S block right here? And don't we always say 2 electrons are in the S block? So that means, hey, beryllium has got a full S subshell. I'm done. I'm full. I don't want to take any electrons because then that throws me into the P subshell, which is higher energy, and I don't want to do that. So that's why there's this little dip right here. Okay, well, what about here in the middle of the P block? There's another one. It's not completely full because here's the P block. It holds 6 electrons. That's completely full. Oh, but the first 3 is half. So what does that mean? Half full affords some stability, right? Because if you remember Hund's rule? Yes, we remember Hund's rule. Yeah, we got to remember those rules. Okay, Hund's rule says that in the 3p orbitals, you know, the 3p orbitals, electrons will want to go 1 in each orbital first. Okay, they don't really like to pair up unless you have to. You know, if you're going to rent an apartment, don't you want to get your own bedroom unless you want to pair up with a roommate? You don't have to, right? Okay, so they pair up singly first. So that's why everybody's like, hey, we're fine. We all have our own spot here, our own orbital. We really don't want to double up with anybody. So that's why a half full affords some stability. So that's why there's the dip there. Okay, so that electron affinity trend's a little different, isn't it? We've got these kind of little dips in here. We don't really have corners where we could say, ooh, the biggest and the smallest. All right, that was electron affinity. Now let's talk about metallic character. You guys know what metals are, right? What are the properties of metals? You know the properties of metals. What's the properties of metals? Shiny, good conductors of electricity, right? Ductile, malleable. Okay, we all know that, right? And you know metals are on the left side, non-metals are on the right. Non-metals don't conduct electricity, right? We know those. Okay, we've talked about that before. But then what are these purple blocks along in here? What are these? Metalloids. What kind of are they like metals or like they like non-metals? What are they like? They're kind of in between, aren't they? So if metals conduct, non-metals don't, these what? Sort of conduct, or we call them semiconductors like silicon. Okay, we talked about that before, haven't we? Silicon is a semiconductor. Okay, so we do need to note where the metalloids are. Notice that aluminum definitely is not. This one is not, and they're changing acetine to a non-metal. They think it's more like a non-metal than it is a metalloid. So, there we go. Well, what's the trend in metallic characters? You're going from left to right. Okay, the metallic character is decreasing. Well, that makes sense because we're getting into the non-metals, right? We know that. Okay, but how about down a column? Let's take down a column. Non-metals, metalloids, metals. What can we say about the metallic character down a column? Increases, right? Okay. Well, you know that same trend down a column is easy to see over here, but the same thing applies over here. So as you go down the column, we're actually becoming more metallic. We're like, what? These are all metals. How can you be more metallic if you're already a metal? Well, we can. So the trend down a column applies over here as well. And we are becoming more metallic. Now, one of those properties of the metals, give me a base that you use a lot in lab. NaOH? Yeah, is that Na, sodium, is that metal or non-metal? Sodium is a metal, yeah? Okay, so what happens is if you have a metal oxide, so metal oxide plus water will produce a base, or a metal hydroxide, which is basic. So this is another thing about metals. So if we become more metallic, aren't we becoming more basic? Yeah, so that's another thing that we can say. So as you go down the column, which is a stronger base? Barium hydroxide or magnesium hydroxide? Barium hydroxide. Does everybody see that? As we become more metallic, we become also more basic. All right, so that's metal oxide plus water is a metal hydroxide. So metal oxides are basic. Well, what happens if you put an acid and base together? What do we get? Acid, base, neutralization reaction produces salt and water. Exactly. So if metal oxide is basic, and I react it with an acid, that's like saying the same thing as acid plus base, and it's going to produce what? Salt and water. Yeah? Okay. So that's metallic trends. Now, if we said that a metal tends to be basic, metal oxides tend to be basic, then what about non-metal oxides then? Yeah, what's a common acid you use in lab? What? Hydrochloric acid? Yeah, so chlorine is non-metal. So the same thing applies. We could say that a non-metal oxide plus water will produce an acid. Okay, so non-metal oxide and water will produce an acid. So if non-metal oxides are acidic, then if I react a non-metal oxide with a base, guess what we get? Salt and water. Exactly. Okay, so those are some of the properties of the metals and non-metals as we talk about that. with trend in metallic character. All right, so does that make sense? Okay, well now this kind of sums up what we're saying. I know we've talked about a lot of trends, but they sort of tie together. Well, we says the size gets bigger, and isn't it easier to pluck off an electron then? Yeah, so those tie together, right? And as we become more or less, if we become less metallic, isn't it harder to get an electron off? It is, isn't it? Okay, so these trends tie together. They sort of help explain each other. So this kind of helps us get an idea and sum up some of the things that we were talking about. Because as we become less metallic, then our electron affinity is going up because it's harder and harder to get that electron off. Okay? Does that make sense? All right. I mean, our ionization energy increases to pull off the electron, but so does our electron affinity increases because that means we want the electron. So ionization energy would be to remove the electron. Electron affinity would be add them, and they're both increasing because isn't that what nonmetals want to do? Yeah, it does, doesn't it? So does that make sense? Does you see how they kind of tie together with our trends? Okay, great. Well, that, and we've already kind of talked about the metals versus the nonmetals. So that finishes up our trends on the periodic table as a scope. So did you guys get all those trends? Yeah, you'll be able to tell me which is bigger, which is smaller, which is greater ionization energy, which is less, which has greater electron affinity, which is less, right? Isoelectronic series, put them in order of size, all that. Awesome! Boy, that was so simple, wasn't it? Okay, that's great. Okay, well, the next thing we want to talk about that finishes up Chapter 7 is the trends of the properties of each group. So we're going to talk about group properties. Okay, what's going on in a group? Okay, so that's what we're going to talk about next. And I think the easiest way to do that with these group trends is we're going to do a worksheet. Okay, so we're going to pass out a worksheet and we're going to talk about it and fill it in. Because there's a lot of groups, a lot of properties for each group. So let's do that. So we're going to fill these in as we talk about it, as we go. Okay. Okay, so everybody got one? Are we missing one? Okay, we're good? All right, so let's talk about these group trend properties, these properties within a group. All right, so let's talk about the first one. You guys know what the name of that group is. Alkali, we remember the names. Now, alkali metals, that's group 1A. Now, we know that hydrogen's not a metal, right? Does everybody remember that? Okay, so we know the name of that group. This group has one valence electron, right? Group 1A has one valence electron. Okay, now they're very soft. These metals are very soft. You can just like cut them with a knife, like cheese. Okay, it's a very soft metal. You can just cut them. Very, very soft. So let's talk about density. All right, what do you see is the trend here in the density? Density is increasing, yep. Let's talk about why it's increasing. What's density defined as? Mass divided by volume. Okay, so as you go down the column, what's happening to mass? It's increasing. But what's also happening to volume? It's increasing. Okay, but the mass is outpacing this increase in volume, so in other words, density is increasing. Well, we know the mass is increasing and the volume is increasing, so density is increasing. All right, so as you go down a column, density is increases. Now, we remember our trends in atomic sizes, so let's put our size back up here. What did we say is the biggest corner? We said was which one? Bottom left. Okay, this is largest. And this one is smallest. All right. So as you go down the column, what happens to the size? It increases. Okay, we know that. Size increases as we go down the column. Now let's put up our ionization energy one. Okay, this is first ionization energy. Okay, so do you remember first ionization energy? Which is the lowest? Which one? Okay, this is the lowest. Bottom left. And which one's the highest? Top right. That's the highest. Okay, so as you go down the column, what happens to your ionization energy? Decreases. Okay, very good. Now, when you excite these elements, they are going to produce characteristic colors. You know how fireworks, we shoot fireworks and we're like, ooh, ah, so pretty, look at the blue, look at the red. Okay, those are from different elements. When you excite them, they give off different colors. So we're going to see different colors when you excite them. Besides, we do the hydrogen and the helium lamps, right? This atomic spectroscopy, you'll see the different colors when you excite them. So when you excite them, they produce different colors. We talked about Bohr's model. Okay. Now, these are very reactive. You're not going to be able to find them in laying around outside. Like sodium. Sodium reacts with water. So if you have a chunk of sodium on the sidewalk, is that going to happen? No. It reacts with water. Water in the air even. Water vapor in the air and just reacts with very things. Okay, so they're found in nature only as compounds, but we have sodium and potassium in our body. Does that mean we have the metals in our body? It's the ions, isn't it? It's the sodium ions, potassium ions. Okay, because these can react with a lot of things. Now, let's talk about reactivity. What happens to the reactivity in a column? All right, so let's see if we can watch this one.
Now let's see another reaction of the alkaline metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkaline metals react with water in the same way. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the groove. Let's try cesium, our fifth alkaline metal.
Okay, so what can you tell me about the reactivity going down a column? It definitely increases. Yeah, it's like, whoa, with water? Things react with water? Yeah, increasingly terrible. Okay. All right, so, okay, well, let's talk about why is that? Why does that happen? Okay, why would that occur? So why does reactivity, okay, so as we go down the column, let's put that up here. This is alkali. Okay, as we go down the column, what are we saying with reactivity? Okay, so reactivity increases. Let's write that down. Reactivity increases down the column. Why? Why? What happens when a metal reacts? What's the metal doing with its electron? Just giving it away, right? Yeah, so it's giving it away. We're like, hey. So the more we give it away, the easier it is to give it away. Wouldn't that make me be more reactive? Yeah, the easier it is to give it away, that would help me be more reactive, right? And we know reactivity increases down the column. So let's talk about removing an electron. What was that? Was that electron affinity or ionization energy? Ionization energy. So what happens to the ionization energy as you go down the column? Yeah, what does ionization energy do as you go down the column? It gets lower, right? Lower down the column. Yeah, so it's there you go. She's like, there it is, on the chart. So, yeah. So ionization energy, as you go down the column, what happens to it? Decreases. And isn't ionization energy removing an electron? So isn't it easier and easier and easier for the electron to leave? So if it's easier and easier for the electron to leave, doesn't that make me tend to be more reactive? Yes. So the logical. So the reactivity increases because ionization energy is doing what? Decreasing. Okay, that's why it gets to be more reactive. As you go down the column, we are becoming more and more reactive as we see. Woo, that cesium was fun, wasn't it? Woo. All right, well, let's talk about the second column. You guys know group 2A, that's what called alkaline. Now, alkaline metals are harder. I can cut the alkali metals with a knife. I can't do that with the alkaline earth. They're much, much harder. Okay, so these are harder. And as you can see from if they're harder, then they're going to be more dense, aren't they? Okay, so they're denser than alkali. Alkali I can cut with a knife. Can't do that with the alkaline earth. Now, so they're more dense than the alkali metals, but again, what's the trend in density as you go down the column? Density it's increasing, right? Okay, so density increases down the column, and they're more dense than what we saw in group 1A. All right, we know about radius. What happens to the radius as you go down the column? Increases. Okay, so radius is increasing as you go down the column. Okay, but what if I'm going from group 1A to group 2A? So if I'm going from group 1A to group 2A, 1A to 2A, what happens to the size? Decreases. So these are smaller, more dense, aren't they? Okay, they're smaller and more dense. So we know size decreases. Okay, what about ionization energy? Oh, we know that again. Ionization energy, as you go down the column, it decreases. All right, so what happens to ionization energy between group 1A and group 2A, though? Okay, it increases. Very good. From group 1A to group 2A, we're going to be increasing, aren't we? Ionization energy increases. Okay, awesome. So they have group 2A has higher ionization energies, doesn't it? Group 2A has higher ionization energies. And these also emit a characteristic color when excited. Okay, so let's take a look at their reactivity. So let's do reactivity here. Okay, do you see that barium is the farthest one on the right, and it's the one that's on the lowest? And then we go strontium. So barium is at the bottom of the column. This is calcium, so we're just putting them in water. And at the very top of the column, okay, that's magnesium. Okay, so, wow. Okay, so what did we see about the reactivity going down the column? It increases. It does increase. Okay, but how does it compare, though? Let's take a look at this. how does it compare? Let's look at our, remember our cesium? Remember cesium was like, boom! Okay, well right next to cesium is barium. Well, how does barium compare? Not, yeah. 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 Okay, so a couple things here. For alkali earth, so let's put alkaline up here. Okay, alkaline, what happens to the reactivity as you go down the column with the alkaline? As you go down the column? Okay, so reactivity increases, we know that, and for the same reasons, right? Because ionization is decreasing, we know that. Okay, but now let's compare group 1A and group 2A. Well, which one was the more fun? Group 1A was more reactive, isn't it? Okay, so reactivity, as you go from group 1A to group 2A, what's happening to the reactivity? It's decreasing. So let's put that down. Reactivity is decreasing. Great. Now, can you tell me why? Ionization energy is... Okay. Woo! Ionization is increasing, isn't it? Very good. So the reason is ionization energy is increasing. All right, make sense? Okay, super awesome. Okay, so that's reactivity. Now let's go to the next column, which is the chalcogens. Okay, so we've done this now a few times, so I bet you can fill out. So I want you to take a few minutes, work with your partner. If you got the PowerPoints, pull that up, and I want you to fill in group 6, 7, and 8, and then we'll go over them. Okay, so if you got the PowerPoints, pull those out, work with somebody who's got one, talk it over with your neighbor, fill out the rest of that sheet, and then we'll talk about it. Okay, so fill them all in, and then we'll talk about them. Do 6A, 7A, and 8A. Okay, turn around, check with your neighbor, see if you can figure out what those are. You guys filled out the chalcogens? Yeah? Okay.
I always have a hard time saying that. I don't want to say it.
You want to say but it's like a K. Yeah, chalcogens. I know, yeah. I know. Oh, we won't talk about the definition of allotropes.
Okay.
If you don't know that, we'll talk about it.
So yeah, it's going to increase electron. Yeah, look what it says there. Reactivity decreases by
Start at the middle of the table. Increases on surface, affinity increases, and reactivity down.
Yeah. So does it increase electron or down? Yeah, that's what I thought. It was all so clear. I'm sorry. Oh, density increases still down. Those jokes.
Okay, so you guys finishing up the last one? The halogens? I mean the noble gases?
So we had like down the column, the reactivity increasing. That's for the alkali, alkalis. And it's going to be the same for the halogens, right? No?
Can you imagine? I was messing with that because.
We'll talk about it.
Okay, because
Yes.
Okay, give you about another minute or so to finish up that, and then we'll talk about it. How you guys doing?
We're going.
Okay, fill in the last one. Noble gases, right?
Yeah.
Okay, so did we get them all? You want to go over them? See what you got? All right, let's go over them. Okay, so let's start with the chalcogens. Did you guys fill it all in for the chalcogens? All right, well, let's see. It contains three types of elements. There are three types of elements, which would be what kinds, did we decide? Non-metal, metalloid, and metals, right? Don't they contain all three? You got the metals, the metalloids, the non-metals. All right, there's that one. Now, polonium, what do we know about polonium? It's radioactive. The further you get down into the periodic table, the more and more reactive elements you're going to have. And we'll talk a lot about that reactivity, nuclear reactivity, and all of that when we're radioactivity when we're in 1412. Okay? But right now we understand that polonium is radioactive. What about density? Increases. We already know that. Atomic radius, we should get that, right? Yes, it always increases down a column. How about ionization energy? We should know that one too. Decreases down a column. Yes. Now they form allotropes. So what's an allotrope? Okay, an allotrope, you have the same element. Okay, it's the same element in the same state, but different forms. So it's the same element, same state, different forms. They have different forms. So what do you mean by different forms? Well, let's take oxygen. You've got O2, which is what we breathe, and we have O3, which is ozone. Now they're both oxygen, so it's the same element. They're both gases, same state, they're both gases. But O2 and O3, we want to breathe O2. Do you want to breathe O3? No, we do not. That's bad. Now we need ozone, of course, in the upper atmosphere to protect us and all that from rays and things, but we don't want to breathe that, so they're different. Does that make sense? An allotrope is the same element, same state, different forms. Okay. All right. Let's talk about 7A. What do you know about 7A? That's the halogens. Okay, remember when we're talking about our liquids, which two elements are liquids on the periodic table? Bromine and mercury. So the only column that has gases, solids, and the liquid then would be 7A. Do you see that? You've got the gases in red, then you've got bromine is the liquid in blue, and then you got the black. So do you see any other column that has all three? No. So the halogens have all three of the states. They've got gases, solids, and liquid. So they got the three states that matter. And of course, you know they're part of the 7 diatomics. We know those. We remember the 7 diatomics, right? Okay. Now again, you know what density does. Increases down the column. You know about the size. Okay, radius increases down the column. We know that. Size always increases down the column. Ionization energy. What's ionization energy doing as you go down? Decreases. That's right. Now, these will dissolve in water to give us what? Do you remember those binary acids we talked about naming? We can say hydrohalic acids. Okay, those are those binary acids, right? You remember that? HCl, hydrochloric acid, hydrobromic acid, hydriodic acid. We even named all those way back in chapter 2. So those are those acids. Now, you remember your strong acids? Yeah, do you remember those strong acids? Okay. Are all of those strong acids? No. One of them is not a strong acid. Which one is that? HF. Very good. Okay, so HF is not the strong acid. We're not falling for that, right? Chlorine, bromine, and iodine, they form the strong acids. If you remember our strong acids, of course we do. Yeah, we're going to use that again in 1412, so we need to remember what those are. Yay! Okay. Now, let's talk about reactivity. Okay, that's a little confusing. Let's watch this reactivity. This is... all right. Okay, let's take the sound off of that. Okay, this is reactivity with the halogens. Okay, so this is iodine, right? It's purple. They have characteristic colors. So to get iodine to react with steel wool, we're going to really have to heat that up. So we're starting at the bottom of the column. Okay, we're really heating it up. Okay, then there's bromine. Bromine is a characteristic brownish orange color. Okay, we're just going to heat it a little bit to get it to react. Okay, there's reacting with steel wool. Okay, so as we're going up the column, there you can see it going right there reacting. So we did iodine, we did bromine. It was really hard to get that iodine to react. Okay, now this is chlorine. Are we even having to heat that with the flame? No. Wonder what's going to happen with fluorine. Whoa, we just have to blow the gas on there. We just blow fluorine right onto the steel wool. Just don't need any heat or anything. So what can you tell me about the reactivity then of the halogens? Which one's more reactive, fluorine or iodine? Fluorine. So fluorine is more reactive. So what about that reactivity? Okay, so it increases up the column, or we could say reactivity decreases down a column. Either way you want to look at it. Okay, so if you go down the column, the reactivity decreases. So in other words, it's opposite, isn't it? So the one that's most reactive, so if we put our halogens up here, the one that's, if reactivity increases, then, I mean, as we go up the column, that's where the reactivity increases. So reactivity increases up the column, or you could say reactivity decreases, or, yeah, it increases as you go up the column, right? Or decreases as you go down. Does that make more sense? In other words, fluorine is more reactive, isn't it, than iodine? Okay, so fluorine is most reactive. Reactivity increases as we go toward the halogens. Whoa, isn't that the exact opposite of what we were just talking about? It is. Now, why is that? What did we say metals tend to want to do? Give away those electrons. What does the non-metals want to do? Gain electrons, right? So fluorine's like, I really want those electrons. Scrounging around the house looking for those dollars to bid for that electron on eBay. Okay, so that's why reactivity goes the other way. Because we're not talking about losing electrons anymore. We're talking about gaining electrons. Okay, does that make sense? All right, so that's with the halogens. And the very last column, of course, we know that. That's the noble gases. Are these part of the diatomics?
No.
No. Remember, they don't want to act with anybody else on the periodic table. They're like, hello, no thank you. So they're monatomic gases, and you know about the density. Does what going down the column? Density increases. What about the radius? Increases. Now, we know they don't react a lot. So why not? They're full. Full what? S&P subshells. We're full S&P subshells. Remember we looked at those electron configurations? They're like, hey, we're full. We don't need any more. Thank you. Okay, so they have full S&P subshells. Now, ionization energies are really high because as you get over to our gases over here, ionization is increasing, right? So it's really high. But what happens with the ionization energies within the column? It decreases. Okay, so ionization energy decreases. So if I'm looking down the column, xenon, yeah, it's a little easier to get that electron off of xenon than it is neon, isn't it? Well, we know noble gases don't react with the other elements, but let's say, since it's a little bit easier to get electron off of xenon, what if I paired it with somebody who really wants electrons? And who do we know really wants electrons? Fluorine. Well, what if I put xenon and fluorine together? Do you think fluorine is strong enough to pull that electron away from xenon and get a compound, actually? Yeah, actually, that's true. That's what happens. So we have xenon and fluorine. They actually form a compound. They form 3 stable compounds, and it kind of looks like plastic or ice crystals, doesn't it? Okay, but if you start to go up the column, it's harder and harder to get a stable compound. Okay, and then with argon, you're like, no. Okay, so does everybody see that? Okay, now, one of those is very radioactive, and that would be radon. Radon is very radioactive. Have you heard about radon in Texas? Radon gas? No, not really. Because this is the EPA map of radon zones. Look where Texas is. We're like, hey, we're good. Yeah, we're yellow. We're good. Everybody else across the country starts to get higher and higher into the red zones. That'd be bad. So what's the big deal about radon? Well, radon is radioactive gas. It's naturally occurring. Comes out of the ground. Dissipates into the air. But there's a problem if you live in the other countries where it's red or orange, other parts of the country where it's red or orange, because in our homes, we seal up our homes because we want insulation, air conditioning and all of that. Well, when you do that, as the radon seeps out of the ground, it will seep into your home. So now that you've trapped it, what you're doing is you're just trapping all that gas in your home, and it's radioactive. So people who breathe a lot of that will develop higher incidences of lung cancer because it's radioactive. So we don't want to do that. You don't want to be breathing radon gas. It's radioactive. So what you do is you ventilate your homes. So by ventilating your homes, venting the basements, that kind of thing, you'll let the radon gas dissipate. And it is naturally occurring. It just happens all the time. But if it dissipates into the air, we're fine, and we're not going to have higher incidences of lung cancer.
Is there a particular reason why our region is less than others?
Yes, it's got to do with what the ground is made up of, Up in the upper areas, you got a lot of rock and stuff, and so it's a decomposition product from uranium. So we don't have a lot of that here, so we're like, we got those clay soils. All right, does that make sense? Okay, whew. Well, that finishes up chapter 7. Boy, we just went right through that. All right, so chapter 7, we're done. So you can check with your neighbor to make sure you got all that correct information on your sheet. Are you going to forget to study that? No, of course not. Are our learning objectives covered by that sheet? Yes. Does that mean there's going to be exam questions about this? Yes. Yeah, absolutely. Okay, awesome. Well, let's go ahead and take a break now, and we'll come back and we'll do chapter 8. So we'll be back at 5.